Alright everyone, welcome back. Today we'll be talking about one of the most powerful rules that we have for taking derivatives, which is called the chain rule. So this particular rule, the chain rule, deals with composite functions. Deals with composite functions and adds some, dare I say, versatility to the previous rules discussed. I just want to remind you, so last time we spoke about the product rule. The quotient rule. So these were the two rules that we spoke about last time, if you recall. So the product rule had to do with, if you had the derivative of f times g, if you wanted to find what the derivative is, and that is equal to g of x times f prime of x plus f of x times g prime of x. And the quotient rule dealt with taking the derivative of a fraction like f of x over g of x, and that was equal to g of x times f prime of x minus f of x times g of x, g prime of x, divided by g of x squared. So this was the quotient rule and the product rule. Now, the chain rule helps us solve problems that neither of these rules by themselves can actually solve. So I'm gonna make a little table of some typical functions that you could solve without the chain rule. And then on this side, I'm going to put some functions that you have to solve with the chain rule. There's no other way of solving them. Okay. So without the chain rule, you could solve things like y equals x squared plus 1, or y equals sine of x, or y equals 3x plus 2, meaning you could take, when I say you could solve, I mean you could take the derivative of these functions without using the chain rule. Y equals e to the x plus tangent of x, let's say. So all of these you could solve without using the chain rule. However, if you were given something like this, if somebody comes up to you and gives you, the square root of x squared plus 1, you cannot solve this without using the chain rule. Or y equals sine of 6x, for example. You cannot find the derivative of that without using the chain rule. Or let's say y equals 3x plus 2 to the power 5. This one is interesting. You could solve it without using the chain rule, but it's going to take you forever, and I'll explain why in a few. And finally, let's say e to the 5x plus tangent of x squared. So these ones you cannot solve without using the chain rule. Now, the chain rule is a concept that is not the easiest to explain. However, we will see how the chain rule acts today. The way that I like to think about it is as follows. Let's say, and excuse my drawing skills, but let's say you're stopped at a red light. So let's say there's a car here. Yeah, I can't draw a car for save my life. So let's say there's a car and stop here. And let's say this is your car. You're stopped here. It's like the Flintstones car, right? And let's say you are both stopped at the light. And now let's say that another car comes at some speed down the street. And this third car hits the back of your car. So this third car is going to hit the back of your car at some speed. And because of the speed that he was carrying at the time of impact, let's say he impacted you right here, he propels you forward, your car moves forward, and now you hit the car right in front of you. So you went all the way up here, and now your bumper is up here. And then this car now is propelled a little bit forward as well because of the impact. Well, the car in the back right here did not actually hit the car in the front up here, but the car in the back still had an effect on this car that's in the front. And the reason why this car had an effect is because he hit that some car in the middle. He hit an obstacle in the middle, and that obstacle then was propelled and hit the other car. So we could see that the vehicle that caused the accident, for this vehicle, if you talk to the insurance company, it's still going to be the car in blue, for those of you who drive. That is how I like to think about the chain rule. The chain rule helps us solve problems like this, like tangent of 6x plus, let's say, e to the cosine of x. Here we have a composition of functions. I have 4 different functions within this one equation. What are they? Well, I could say one, let's call f of x just tangent of x, which is just a tangent function. We have g of x, which will just be the linear function 6x. Then let's say h of x is going to be e to the x, just an exponential function. Let's say k of x is going to be equal cosine of x, the trigonometric function up here. I have a y is a composition of all of these functions. Okay? So when you take the derivative of a composition, you are affecting things on the inside. So an example of that will be something like y, like to make it like the 3 vehicle example, something like e to the cosine of 7x. If you were to take the derivative of this, you have 3 functions in this composition. You have e, you have cosine, and you have 7x. So the e, the exponential function, represents the blue car. That's what you want to take the derivative of. Well, when you take the derivative of e, you are affecting the cosine that's up here, and in turn the cosine is affecting the function on the inside, the 7x. Luckily, we have the chain rule that gives us a way of actually evaluating these types of derivatives. So let me just give you the rule for the chain rule, and then we could do some examples so that you could understand more what's going on. So this is the chain rule. Right, so let's say y equals f of u is a differential function. Differentiable function of u, and u is equal to some function g of x, and it's also a differentiable function. Remember, differentiable just means that you could take the derivative, that the derivative exists. But g of x is clearly a function of x. Then the following composition, y equals f of g of x, is a differentiable function of x. It's a differentiable function of x. And the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. I'll explain what this means in a second. Equivalently, we could write this as follows. We can say that the derivative with respect to x of f of g of x is equal to the derivative of f composed with g of x times the derivative of g of x. Okay, so that's the end of the theorem. So basically what this means is that we will take the derivative of the outer function evaluated at the inner function, and we will multiply it by the derivative of the inner function. I'll repeat that again. When we apply the chain rule, we take the derivative of the outer function evaluated at the inner function. In this case, the inner function is g of x, and then we will multiply that by the derivative of the inner function. Repeat that a third time. When we apply the chain rule, we will take the derivative of the outer function evaluated at the inner function, and we will multiply that by the derivative of the inner function. Okay? Before we begin to actually use the chain rule, let's just decompose some compositional functions. We did this in the review for pre-calc as well. So decomposing some composite functions. It's important, and I mentioned this throughout the early stage of the class, it's important that you understand how to decompose function compositions and how to identify what the composition that is occurring is. So for example, most of these are going to be in the form of y equals f of g of x. Let's say you're given, I don't know, let's say y equals 1 over x plus 1. Then I'm going to say that u, meaning the g of x, is going to be equal to, well, the inner function. In this case, the inner function is the function in the denominator, which in this case means that u equals x plus 1. And then the outer function, f of u, is y equals 1 over u. Because you have to realize here I have two functions going on. I have a rational function, meaning I have something of the form a over b. So it's a rational function. And then I have a linear function in the denominator, something of the form y equals mx plus b. So I have two things going on here at once. And you have to realize that one must come before the other. So you first plug in the denominator, and then you have the fraction. Let's do another one. What about y equals sine of 2x? This one is a little bit easier to see because the inner function is simply the linear function 2x. So the inner function here, u, is going to be equal to 2x. That's a linear function. And the outer function is just simply equal to y equals sine of u. I remember, this u is this u. So when you write y equals sine of u, if you replace u by what it's equal, meaning by 2x, you get back to u. This is like one of those problems where, let's say, from like middle school, you have something like 3a plus 7b, and you're told a is equal to 2 and b is equal to 7. Then you just plug in for a and b. So this is a substitution that we're doing. Nothing really fancy yet. Let's look at another one. How about y equals radical 3x squared minus x plus 1? Well, here, the inner function is whatever is inside of the radical. So that is 3x squared minus x plus 1. And then the outer function, let me erase this. The outer function is simply the radical u. And finally, one that could be tricky to be tangent square of x, here your u is simply x, the linear function x. But your outer function is going to be, actually, no, my inner function is tangent of x, not x. There's a square here. So that means that the outer function is x squared, or u squared, since I'm calling it u. So u squared. So understanding what the composition is goes a long way. I'll leave one more as an exercise to see if you can identify what the composition will be. And that will be secant of e to the 3x plus 5. Okay? Let's do an example actually computing a derivative by using the chain rule. So let's find the derivative of y with respect to x for y equals x squared plus 1 cubed. So here, the trick is to first identify what u is, meaning what your inner function is and your outer function is, and then proceed with the actual chain rule. So here, I can clearly see that my inner function is going to be x squared plus 1. So u is going to be equal to x squared plus 1. That means that my outer function is actually equal to, where's my pen? It's going to be equal to u cubed. So I have a cube here. So you have to think about this as what do you do first? You know, PEMDAS says to do whatever's in the parentheses first. So I'll be this inner part. Then goes the exponent. So that's how you kind of know which one is going to be the inner one. The inner one is the one that you compute first. Well, now that I know what u and y are, my outer and inner functions are, I can now apply the chain rule. So let me just rewrite the chain rule for you. The chain rule said that dy dx is equal to the derivative of y with respect to u times the derivative of u with respect to x, which I said, in other words, is the same thing as the derivative of f evaluated at g times the derivative of g with respect to x. So the g of x here is what we're calling u. So we have to find out what the derivative of u is. And we have to find out what the derivative of y is, because y in this case is our f of x. Well, by the power rule, we know that the derivative of x squared plus 1 is simply going to be equal to 2x. The derivative of x squared is 2x, and the derivative of a constant like 1 is 0. Y prime, on the other hand, is going to be equal to 3u squared. Remember, we bring down the 3 and then we minus 1 by the power rule. So now, by applying the chain rule, we have that the derivative of y with respect to x is equal to, let's see, we have f prime of g, so 3u squared, times u prime, which is 2x. So I just follow the rule. F prime evaluated at g times g prime of x. Now, this is not g, this is u. So let's bring back our u. U was x squared plus 1. So let's substitute that back in. So this is 3 times x squared plus 1 squared times 2, times 2x. So I simply substituted back the value of u from up here. And now we can simplify this. So we have to expand this. So this is x squared plus 1 times x squared plus 1 times 2x. And this is equal to, when you multiply this, is going to be x to the fourth plus 2x squared plus 1 times 2x. And then when you multiply the 2x times the 3, you get 6x times x to the 4 plus 2x squared plus 1. And finally, you could distribute that 6x over, and you'll get 6x to the 5 plus 12x cubed plus 6x. And that will be your solution. You don't have to, for the most part, expand all of this unless I tell you to simplify. But this is what the derivative of y is. Okay, so dy dx is equal to 6x to the 5 plus 12x cubed plus 6x. All right. Let's do one more example, or maybe two more, to drive the point home. So let's find dy dx for y equals cosine of 3x plus 5. Okay, so here, what is my u? My u is my inner function. The inner function is 3x plus 5. You should get into the habit of looking at what's in cosine is a function on its own, and it takes in x values or theta values. And on the inside, I have a linear function, which is 3x plus 5. So that's how you kind of tell which one is going to be the inner and which one is going to be the outer. So the inner function is u, that's 3x plus 5. The outer function, y, is going to be equal to cosine of u. Notice that I do not know how to take the derivative simply of cosine of 3x plus 5. I need to use the chain rule for that. But for y equals cosine of u, we actually do know what the derivative of this is, because we covered this a couple of weeks ago. The derivative of cosine of u is negative sine of u. It's the same thing as the derivative of cosine of x. Now, the derivative of u is going to be equal to 3, because the derivative of 3x is 3, and the derivative of 5 is 0. So if we put the chain rule together now, let me just rewrite this. So this is cosine of 3x plus 5. Then by the chain rule, the derivative is going to be equal to f prime, evaluated at g of x, times g prime of x. So that's equal to, maybe I shouldn't use y prime. So this y and that y are not the same. But anyway, this is going to be equal to what f is. So my f prime is negative sine of u. My f prime is negative sine of u times g prime, which is just 3, because that's what u prime is. But now I know what u was. U was simply 3x plus 5. So let's substitute that in. So y prime is equal to minus sine of 3x plus 5 times 3, otherwise known as negative 3 sine of 3x plus 5. Let's do one more example in the chain rule to drive the point home. Let's find dy dx. Chain rule is not going to go away. I mean, every problem that we do from now on may include the chain rule, or maybe solve using the chain rule. Well, find dy dx for f of x. Let's use let's use y. For y equals square root of tangent of x squared plus 3x plus 5. This problem is going to be a little bit more tricky. So here we have u, and just to keep it with the formula, I'm going to use f of x. So, or actually f of u. So u here is equal to the inner function. u is always going to be your inner function, so that's x squared plus 3x plus 5. And f of u is simply equal to the square root of u. Well, here we have three functions actually going on, so we have to be a little bit more careful than what I'm being. So it's going to be tangent of u, and then we have a third function, which I'll call g of x, which is actually equal to, and let me not use x here, g of v, and I'll call this v. So v is equal to f of u, which is equal to tangent of u. And then g of v is going to be equal to the square root of v. The reason why I'm doing this is because this makes our life much easier. So here we have to use the chain rule twice. This is going to be a much more tricky problem to solve. Alright, so first of all, let's take the derivative of u. The derivative of u is going to be 2x plus 3. The derivative of v is going to be equal to, we did this last class, is secant squared of u. And finally, the derivative of g is going to be equal to, this we have to rewrite, so let me actually rewrite it. This is just v to the power 1/2. So this is just the power rule, so this is going to be 1/2 v, and 1/2 minus 1 is just negative 1/2. So this is equal to 1/2 times 1 over v to the 1/2, which is equal to 1 over 2v to the 1/2. They said this was going to be a more challenging problem. But now it's all a matter of putting it together. So now we have the dy dx is simply the composition of this. So which one goes first? Well, 1 over 2v to the 1/2 goes first because that's the outer function. But now what is v? This v was tangent of u. And we still have to multiply by the derivative of v prime because we're doing the chain rule. So we multiply by v prime. Almost forgot about that. So what do we have here? So we have dy dx equals 1 over 2. V is tangent of u. And remember, 1/2 just means the square root. So this is tangent, and u is x squared plus 3x plus 5. So x squared plus 3x plus 5 times v prime, but v prime is secant square of u, but again u is x squared plus 3x plus 5 times, because we did the chain rule with this portion right here, we also have to multiply this piece by the derivative of u, which is u prime, which is 2x plus 3. Something that I'm forgetting to write up here. So you still have to multiply by this as well. So the solution to this problem, which I'm not going to simplify because as you could see it's already a mess, is simply going to be equal to 2x plus 3 times secant squared of x squared plus 3x plus 5 divided by 2 times tangent of x squared plus 3x plus 5. So notice how difficult these problems can get. And it's all a matter of bookkeeping. You have to be able to keep track of all the work that you're doing in order to do the problems correctly. Okay, let's do one more because it was a bit too difficult. I mean, it was pretty good that we did it because it involved 3 different functions. But let's do a simpler one. So let's find dy dx. This is going to be the last example for this video. For y equals square root of x cubed plus 5x squared. just because I wanted to do it with the square root again. Right, u, the inner function, is the cubic x cubed plus 5x squared. That means that f of x is going to be equal to the square root of u. F of u is going to be equal to the square root of u. U prime, you should always find the derivatives first before putting it together on the formula. It's going to be equal to 3x squared plus 10x. The derivative of x cubed, you bring down the 3, you minus 1, so that's 3x squared. The derivative of 5x squared, you bring down the 2, you multiply by the 5 because of the constant multiple rule, so that gives you 10, and then you minus 1, so that's x to the first. The derivative of f of u, again, you rewrite this as u to the power 1/2, so it's easier to see it. You multiply the 1/2 to the front, you bring it to the front, so that's just 1/2 times, and then you minus 1, u to the minus 1/2. And again, just rewrite it as 1 over 2u to the 1/2. So that's what f prime of u is. And now we know that dy dx by the chain rule is going to be equal to f prime evaluated at g of x times g prime of x. And again, we have these values now because we computed all of them. So it becomes very easy to put them in. F prime of u is this. It's 1 over 2u to the 1/2 times g prime of x. In this case, our g prime of x is what we're calling u prime, and that's going to be equal to 3x squared plus 10x. But this problem was given to us in terms of x's, so we have to turn that u back into what it originally was, which is x cubed plus 5x squared from up here. So this is equal to 1 over 2 times x cubed plus 5x squared to the power 1/2 times 3x squared plus 10x. And you could simplify a little bit this a little bit more. You could bring this numerator together. So this is 3x squared plus 10x divided by 2 times the square root of x cubed plus 5x squared. So that's what the derivative is equal to. And this is the chain rule. So to summarize once more, if you're taking the derivative of a composition, then that's the same thing as taking the derivative of the outer function with respect to u and then multiplying it by the inner function with respect to x. And u represents the inner function here. Alright everyone, thank you for your time in this video.